Hello once again, this is the Pencrest High School AP Physics 1 video series. This is video 7E, Rotational Kinetic Energy and Work. Now we've already seen when we did work in energy that kinetic energy is the energy of motion. Objects that are rotating obviously are in motion and therefore they also have kinetic energy. We're familiar with the standard kinetic energy formula which we use for linear motion. Knowing the analogies for mass and velocity, you should be able to predict the formula for rotational kinetic energy. In the linear sense, K, capital K equals 1/2 mv squared. M is the mass, V is the velocity. In the rotational sense, we still use the symbol K. It's still kinetic energy, but the formula is 1/2 I omega squared. I, rotational inertia, is the analogy for mass, and omega, angular velocity, is the analogy for V, for linear velocity. So kinetic energy equals 1/2 I omega squared. Note that the rotational inertia is measured in kilograms times meters squared. Omega is measured in radians per second. When we multiply them, we square the radians per second. When we multiply them, the radians go away, again, kind of magically because we want them to. And we are left with kilogram meters squared per second squared, which are Newton meters or joules, which of course is appropriate units for energy. Now also recall the formula for work done by an applied force. Work done is FD cosine theta. The rotational analogy for force is torque, and we know that the rotational analogy is angular displacement. So when we look at these two formulas, work is FD cosine theta for linear forces, and for rotational, the work done is torque times the angular displacement theta. So we should emphasize that the theta in these expressions are very different. For linear work done, that theta here refers to the angle between the force and the linear displacement. In rotational work done by torque, theta refers to the angular displacement in radians. The units for torque, of course, are newtons times meters, which means they're already set up to provide units of energy. The radians for theta, in this case, disappear because we want them to. And we are left with units of work, units of energy, which is what we want. You can think of the formula for rotational work done this way. If you apply a net torque, tau, such that the object rotates through some angular displacement theta, the amount of work done, and therefore its rotational kinetic energy, would be equal to tau times theta. Recall that work done is the change in the energy state of the system. So it either adds or removes energy from a system of objects. If the net torque is in the direction of the motion, we would say that the work done is positive, and the angular velocity omega would increase. The work done, the positive work done, would come out as additional rotational kinetic energy because the omega gets bigger. If the net torque is in the opposite direction to that of the motion, the work done would be negative. The angular velocity would decrease, and the kinetic energy would also decrease because the negative work done removes energy from the system. So the idea is the same. So let's take a look at a problem that we saw already. We analyzed this from a Newton's laws and kinematics standpoint. We have a disk here as a mass m/2, radius r. It's got a string wrapped around it connected to a hanging mass m. The mass starts from rest. We're going to add that the height is 5r, 5 times the radius above the floor. And we're going to look at this from an energy standpoint. So when we look at the picture we're looking at here, this is the initial conditions, or point A. The mass M has gravitational potential energy equal to mgh at the starting point. It's going to start from rest, so it has no kinetic energy initially. You might think also that the disk has gravitational potential energy. The disk is not going to move vertically up or down, so it's not going to change. Its gravitational potential energy isn't going to change. Wouldn't be wrong if you included it in your energy equation, but it's going to appear on both sides of the equation, so it would cancel. Again, the pulley is going to rotate, but it's not going to move up or down, so its gravitational potential energy won't change. So as the mass falls, you would describe point B as the point when the mass reaches ground level down here. When we set up our energy equation, here's mgh, hanging mass times g times its height, 5r. We're going to take this as h equals 0. On the right, just as the mass is about to hit here, we've got two kinetic energy terms. We have a linear kinetic energy term that is associated with the linear motion of the hanging mass, so 1/2 mv squared. We also have a rotational kinetic energy that's associated with the disk, 1/2 I omega squared. So the gravitational potential energy in the initial case is translated into kinetic energy of both the linear, the hanging mass, and also the disk. Now we know that rotational inertia of a disk is 1/2 mr squared. We'll substitute that into the right side of the equation. The linear velocity of the hanging mass is related to the angular velocity of the disk, such that v equals omega times r. Now this comes about because, again, when we look at the disk, the string as it falls, its linear velocity is going to be the same as the linear velocity of the outer edge of the disk as it rotates. So we already know that the linear velocity of the outer edge equals omega times r. So again, we're making the assumption that the string does not slip on the pulley, and that's a good assumption to make. So we're going to replace omega with v over r. We're going to replace I here with 1/2 mr squared, making note that the mass of the disk is m over 2. And we're going to replace those things, and it's going to look something like this. We still have the linear kinetic energy term, and now we have, here's the 1/2, here's I, where the rotational inertia is 1/2 mr squared, 1/2 times m over 2 times r squared. And then we have omega squared replaced with v squared over r squared. We're going to simplify that a little bit. We'll find that the r's will cancel here on the right, and we end up with 1/2 mv squared plus 1/8 mv squared. We'll do a common denominator, put those together, we'll get 5/8 vb squared equals g times 5r. The m cancels on both sides, and we get a pretty simple expression for the final velocity of the hanging mass as it reaches ground level. What we would find is, once we have that final velocity, we could then use the relationship between the linear and angular velocity to figure out the angular velocity of the disk. We could then use that to figure out its rotational kinetic energy and so on. So again, this is another approach to a problem that we've already seen from a work and energy standpoint. Okay, so that's it for work and kinetic energy. Next up is angular momentum. Until then, enjoy, and I'll see you again next time.